This experiment is a bit different than those we've previously encountered. Fundamentally, we are now working backwards. In previous experiments, we've input known forces acting upon an object into Newton's second law in order to predict the future motion of that object. Now, we are going to use data collected through observation of an object's motion and use that to determine the forces acting upon the object. We will use our observed data of a star circling a black hole to determine the net force acting on this star. We will then use our understanding of the momentum principle to determine the mass of the black hole. With this observed motion, we will use 3 position points to determine 2 velocity points. We will use the 2 velocity points to determine 1 momentum point. This will be repeated continuously throughout the duration of data collection. Then, we will use all the different momentum points, which were previously calculated, to determine the change in momentum, as displayed visually in this picture. We will then use our understanding of the momentum principle in the concept that change in momentum with respect to time is equivalent to the net forces acting on an object to determine the sum of all the forces acting on the star. Once Fnet has been determined in this manner, we can begin to understand how we will calculate the mass of the black hole. We are told that gravity is the only force acting on the star, so we can say that Fnet is equal to Newton's universal law of gravitation. With g being our constant, approximately 6.7 times 10 to the negative 11, mass 1 being the mass of the star, mass 2 being our unknown mass of the black hole, and r being the difference in position between the star and the black hole. Through this experiment, we will actually find that the mass of our black hole is equal to about 2.38 times 10 to the 31st kilograms. Now we must indicate all of these physics concepts previously discussed to our VPython code. We first set our initial conditions. We input the mass of the star, the time step, in this case 1 year expressed in seconds, and lastly define g, which will later be used in our calculations. In a separate location, we indicated the initial position of the black hole. Now we indicate how the code will determine change in position and how this can be turned into a velocity. As we know, velocity is equal to change in position over change in time. And this is what we see explained in this section of the program. To understand this section of the code, it is helpful to think about what we previously discussed, where 3 position data are used to create 2 velocity data. Now we must explicitly state how to solve for the initial and final velocities. As you can see, the initial velocity is described by the -1 as the data point just previous to the data point designated final velocity. We then can specify that P initial is equal to the star mass times the initial velocity. The same process is true for P final. Lastly, in this section, we indicate that the delta of a certain quantity is equal to the final minus the initial, as we show here for delta V and delta P. In the first line of this section of the program, we are defining dp dt. We know that this is the change in momentum with respect to time, so we specify that dp dt is equal to delta P divided by delta T. Next, we use Newton's second law, as we discussed in our introduction, to allow us to set Fnet equivalent to our value of dp dt. In the following lines, we are determining the parallel and perpendicular components that make up dp dt, and thus the parallel and perpendicular components that make up Fnet. These are mainly important for the arrows used to indicate direction in the model of our forces. Now, here's where we truly work to determine the mass of our black hole. We must remember the principles we set forth in our introduction. We know, by observing the changes in position, that we can determine the change in momentum. We know that because of the momentum principle, with this previous information, we can determine the net forces acting upon the star. And we know that because gravity is the only force acting on the star, that we can set Fnet equal to Newton's universal law of gravitation. First, we specify that r is the difference in position between the star and the black hole. Then, given that we know the constant, the net force, the mass of the star, and the difference in positions, we are able to rearrange the variables using a little algebra to solve for the mass of the black hole. Now it is time to run our code. As we can see, we run the code and the designated arrows represent the forces acting upon the object, the star in this case. We get the result as expected. To reiterate, this is all possible because of what we know about the momentum principle, or Newton's second law. we know that we can relate change in momentum to the net forces acting on the object. With this, we are able to find F net. And because there's only one force acting on the object, we're able to set F net equal to our g m1 m2 over r squared. It's important to understand what these variables mean. For instance, if they're equal to each other, then what is the difference between dp dt and F net? Well, the momentum principle is so powerful because it's able to link two very different kinds of things together. The best way to summarize this relationship is by explaining that the momentum change is caused by the net force. Now, what if? Imagine a black hole whose mass you found was removed and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? The answer is yes. As we've previously said, we know that dp dt is equal to F net. We also know that F net is equal to the universal law of gravitation. And we also know, as the star is rotating in a circle, that dp dt is equal to the centripetal force, or mv squared over r. With all that information, we can say that the gravitational force is equal to the centripetal force. Now, after canceling variables algebraically, we can show that the mass of black hole 1 is equal to r1 v1 squared over g, and the mass of black hole 2 is r2 v2 squared over g. If we divide one by another, the only unknown variable we'll be left with is the mass of the second black hole.